This video discusses well-formed formulas and sentences in QL. Before we get into the details of QL, let's review how it worked for SL. Recall that for SL, we could define a well-formed formula, or WFF, in this way. Every sentence letter counts as a well-formed formula of SL. Then, if you have some well-formed formula, then putting a negation in front of it makes a new well-formed formula. If you have two well-formed formulas, then you can make new ones by putting parentheses around them and putting a conjunction between them, putting parentheses around them and putting a disjunction between them, putting a parentheses around them and putting a conditional between them, or putting parentheses around them and putting a biconditional between them. Then we said that an expression of SL is a well-formed formula if and only if it could be built up by repeated application of those rules. That turns the rules into a definition. Finally, an expression of SL is a sentence if and only if it's a well-formed formula. This means that the definitions of a well-formed formula and a sentence were basically the same in SL. In QL, things will be a bit more complicated. In QL, we start with a defined list of symbols. We have the predicate letters, A, B, C, all of the capital letters. We have constants, little a, little b, all the way up through little w. We have variables, little x, little y, and little z. We have the sentential connectives, negation, conjunction, disjunction, conditional, biconditional. We have the quantifiers, a universal quantifier and an existential quantifier. And we have parentheses. Anything made out of these symbols is an expression of QL. The lowercase letters, the constants and variables, are called terms. A predicate followed by the right number of terms is a well-formed formula. What I mean by that is that a one-place predicate, like has a good bagel shop, needs one term. A two-place predicate, like is larger than, needs two terms. And recall that we can have three-place predicates, four-place predicates, or even larger predicates, at least in principle. So, to put it more precisely, an n-place predicate followed by n terms is a well-formed formula. For example, if H, B, and C are one-place predicates, and L is a two-place predicate, it gives us all of these well-formed formulas. These are called the atomic formulas of QL because they're the smallest pieces that we can talk about. We might have had in mind that capital B would mean has a good bagel shop, and little a would be Albany, but that's just what we had in mind in translation. In QL, B is just some predicate that might or might not apply to some objects, and little a is a constant that picks out some object. Now, just as we did in SL, we can build more complex sentences by using the sentential connectives. If you have a well-formed formula and you put a negation in front of it, you get another well-formed formula. If you have two well-formed formulas, you put parentheses around them and a sentential connective between them, the result is a well-formed formula. Those rules let us build up long formulas, like this one, much in the way we did in SL. But what about quantifiers? If you have a well-formed formula, what about putting for all x in front of it? If P is a one-place predicate, then Px is a well-formed formula. And it's okay to put for all x in front of it. For all x, Px is also a well-formed formula. It says that everything's a P. But what about for all x, Pa? It would be weird. It would say that everything is such that A is a P. And that really wouldn't make much sense. The variable is only introduced to go with the quantifier, and it's not doing anything here. Perhaps even worse, what about for all x exists x Px? The variable is introduced as an every for all x, and then it's introduced again as a sum exists x. We could make up ways of understanding this, but it's kind of a mess. So what we're going to do is put a restriction on when you're allowed to put a quantifier in front of a well-formed formula to make a new well-formed formula. Here's how it goes. If you have a well-formed formula and it contains at least one occurrence of a variable, and it doesn't have a quantifier for that variable yet, then for all x put in front of it produces another well-formed formula. So for all x PA doesn't count as a well-formed formula. PA is a well-formed formula, but PA doesn't have an occurrence of x in it. And for all x exists x px, also not a well-formed formula, because although exists x px is okay, it already has a quantifier for x. It has an x quantifier saying this is how you're supposed to read and understand x in the formula. So you can't put a for all x in front of it to make a new well-formed formula. You can do things like this, though. If you have exists x lxy, there's an occurrence of y in it. It doesn't have a y quantifier yet, so you can put for all y out front and produce a well-formed formula. The existential quantifier works in the same way. If you have a well-formed formula, if that formula contains at least one occurrence of a variable x, and it doesn't contain an x quantifier yet, then you can put exists x in front of it, and the result is a well-formed formula. So now we have rules to start with the atomic formula, to use the sentential connectives to put the pieces together, and to add quantifiers. We make these rules a definition by saying that an expression of QL is a well-formed formula if and only if it can be built up by repeated application of the rules. Well-formed formulas are the meaningful expressions of the language. The sentences are the expressions which have truth values. Consider the expression px, where p is a one-place predicate. It counts as a well-formed formula. It's meaningful. And it needs to, because it can be used to build the sentence for all x px. Nevertheless, px doesn't have a truth value. It's not itself a sentence. The x in px isn't the name of some individual who might or might not be a p. Instead, it's a placeholder or an empty blank. Without a quantifier, we don't have instructions on how to fill that blank. The upshot is that we have well-formed formulas that aren't sentences. So we're going to need two separate definitions. Having defined a well-formed formula, we now need to say which of them count as sentences. And for that, we're going to need a few extra conceptions. The scope of a quantifier is the subformula for which it is the main logical operator. Here are some examples. In the first formula at the top, the scope of the exists x is the subformula px. In the second formula, in the middle, the scope of the for all x is px arrow qx. In the third formula, the scope of the exists y is everything in the square brackets, and the scope of the for all x is everything after the for all x. This allows us to say that a variable is bound if it's in the scope of a quantifier for that variable, meaning that there's a quantifier telling us what to do with that variable. So a variable is bound if it's in the scope of a quantifier. A variable is free if it's not bound. If we look back at our examples from earlier, most of the variables are bound. There's only actually one free variable, the x, in the middle sentence. And in fact, only the final x, the first occurrences of x, are inside the scope of the for all x. But that last one, in LCX, is a free variable because it doesn't have any quantifier telling us what to do with it. So a sentence of QL is a well-formed formula with no free variables. Maybe it has no variables at all. Maybe the variables are all bound. But to repeat, a sentence of QL is a well-formed formula with no free variables. Here are some examples. PA is a sentence because it just doesn't have any variables at all, nonetheless any free ones. For all x, px is a sentence because the x in px is bound by the quantifier for all x. And exists x px, arrow for all x qx is a sentence because the first x in the px is bound by the exists x, and the x in qx is bound by for all x. So there are no free variables, and these are sentences. We saw earlier that px isn't a complete thought. It doesn't say whether x is everything or something. Now we can say, technically, that px isn't a sentence because the x in px is a free variable. If you look at the second example, nx arrow for all x qx, the first x in nx is a free variable, and so it's not a sentence. Even though the x in qx is bound by the for all x, the whole formula doesn't count as a sentence because it has one free variable. Looking at the final example, for all x lxy, the y is a free variable, and so it's not a sentence. Finally, we're going to adopt notational conventions. And these notational conventions are exactly the same as the ones we adopted for SL. You can use square brackets as parentheses. You can leave off parentheses around an entire sentence. You can leave out parentheses in a serial conjunction, this and that, and that, and that. You can leave out parentheses in a serial disjunction, this or that, or that, or that. We adopt these to make life easier for ourselves, but they really aren't a change to the official definitions. Here's a practice exercise just to make sure you understand the video. There are 6 expressions of QL on the screen. For each of the expressions, is it A, a sentence of QL, B, a well-formed formula but not a sentence, C, not a well-formed formula? Try to work these out. If you can answer these correctly, then it's a sign that you understand the material we've covered in this video.